Hello, I've had another request to try and explain enthalpy changes for paper 1. So let's have a look at what an enthalpy change is. Enthalpy means heat. So it's a heat change, an enthalpy change or a heat change. It's given by the symbol delta H. Delta meaning change, it's the capital letter D, Greek capital letter D, because Greeks came up with this idea first. So enthalpy or heat change during a reaction. And what it is it's the heat change at constant pressure, because pressure can affect heat changes. Okay, if you go to the top of Mount Everest, water doesn't boil at 100 degrees C, so pressure affects heat and heat changes. So we have to do it at constant pressure. It's also for 1 mole as well, so that's not recorded in the definition, but you work out the heat change for 1 mole. Because if I was to say, for example, describing how wood as a fuel, how much heat that gives out, if I burn a match or I burn a bonfire, they're going to give out different amounts of heat. But they're both essentially wood, but they give out different amounts of heat because I've got different amounts of wood. So I need to standardize to make it a fair test of how good wood is, say for example, at a fuel, and how much change it gives to the heat, the temperature of the surroundings, how much heat it gives out, because it's dependent on the amount of wood. So we use 1 mole as a standard. So enthalpy change is a heat change at constant pressure, and it's measured for 1 mole of the substance that's being burned or combusted, or reacted. Okay, reactions can give out heat. They're called exothermic reactions, and in that case, delta H, the heat change or the enthalpy change, is negative. So an example of an exothermic reaction may be something combusting, something burning. Okay, a reaction which can be it takes in heat, endothermic, is delta H is positive. So an example of something that takes in heat might be ice melting. When you put ice onto your hand, it melts, and it needs energy to melt, so it draws heat from your hand. So something that's endothermic takes in heat, usually to break bonds. So say for example, water going from a solid ice cube into a liquid form is breaking the intermolecular bonds, needs some heat to do that, so it absorbs the heat from your hand, takes in heat. That's endothermic, and the delta H is positive. We're going to work out why they're negative and positive in a minute. I'll show you that. Okay. The next thing you need to know is that an enthalpy change, delta H, is the energy needed to make the products divided by the energy, so take away the energy needed to make the reactants. Okay, and we'll come back to that in a minute. So we're looking at products and we're looking at reactants. Okay, products take away reactants. Energy of products take away energy of reactants. Okay. A little example of how you might think about that is, okay, if I go out for the night and I've got £20 in my pocket, and I come back after that night out and I've got £5 in my pocket, how do I work out how much I've spent? How much money I've now got? Went out with 20, came back with 5. I take the product, which is what I end up with, my £5 note, and I take away what I started with, £20. 5 subtract 20 is minus 15. I am now £15 poorer than I was before I went out for the night. Okay, so that's why you do products take away reactants. What you end up with, a £5 note, take away what you started with, that's your reactants, your £20 note, and you work out the change in heat, change in money. So the same principle applies. EA is the symbol given for activation energy. That's the minimum amount of energy to get a reaction to start. So if you imagine for something like a firework, which is extremely exothermic, going to give out heat, it actually doesn't give out heat until you give it a little bit of energy. Same for a car. A car engine will get very hot when it burns its fuel, whether that be diesel or petrol. Yeah, but to get the diesel or petrol to burn and give out heat and to drive your car, it needs a little bit of energy to get it started, and that happens when you put your key in the ignition. The battery gives it a spark of energy to light the fuel. So that's called the activation energy, the minimum amount of energy to get a reaction to happen. ECAT is the activation energy, the minimum amount of energy for it to make a reaction happen when a catalyst is present. Remember, a catalyst can speed up a reaction, although we've got a different definition for a catalyst in a minute. What does a catalyst do? Okay, so at GCSE you may say something along the lines of a catalyst speeds up a reaction without being used up, or a catalyst speeds up a reaction and is reformed at the end, and that's fine. But there's a better A-level definition. What a catalyst does is it lowers the activation energy. It lowers the amount of energy that is needed to get a reaction to occur. And it does that by providing an alternate reaction route, a different way of the chemicals combining to, say, for example, make a product. A good example of that may be something like a catalytic converter, a metal inside your car exhaust. You've got two gases that combine, two toxic gases in your car exhaust, one called nitrogen monoxide, NO, and one called carbon monoxide, CO. Those two, if we can get them to react, will make two gases that are not quite as poisonous, nitrogen, which is in the air anyway and isn't poisonous at all, and carbon dioxide. Not poisonous, causes global warming, and that's the problem with cars, but not poisonous. Okay, so we've got to combine two gases. Now, normally the reaction route would be that we hope that those two gas molecules collide with each other. But what a catalyst does is it lowers the actual amount of energy needed for those two to combine by providing an alternate reaction route. So inside your catalytic converter, there's a metal called platinum. We coat it on a ceramic like a china base, so we don't need too much platinum, and just surface coat it to increase the surface area and reduce the amount of platinum that we actually need. And on the surface, the platinum bonds the two gases close together and it brings them together. Yeah, it's like bringing two people together on a date. You've got a better chance of them then having a relationship, yeah, or liking each other, if you bring them together. That's called providing an alternate reaction route. So bringing things together. So a catalyst lowers the activation energy, that's the minimum amount of energy needed for a reaction to occur, and it provides an alternative reaction route, a different way for the particles to come together. It may be something like a metal catalyst combining the particles on the surface to bring them closer together and help them to collide and react with sufficient energy. Okay, let's have a look at an energy diagram. The reactants are at this energy. The scale going up the side that you don't see here is the amount of energy. So they are on this amount of energy going up. The reagents should really say reactants. This is not a great diagram. Okay. Now, they may form products. Okay. But to get them to react, let's say this is a firework. Okay. The firework needs some energy to get it to react and to give out heat. So we have to give it some heat. Usually light it with a match, and when we give it some heat, which is called the activation energy, so going up on this scale, up the y-axis is energy, so I have to give it some energy, and then when I give it sufficient energy, which is EA, the activation energy, then it's off. It's going, it's shooting off into the sky, giving out lots and lots of heat on its own. It doesn't need me to light it anymore. In actual fact, it needs me to stand back for safety reasons. So now it's starting to give out energy on its own. I've given it this amount of energy, the activation energy. It's sprung into life. It's starting to react as a firework. Now it starts to give out energy as it shoots off into the sky, and it's giving out energy, and it's giving out energy, and it's giving out light energy and heat energy, and it's exploding in the sky, and it's giving out lots and lots and lots of energy. And by the time it finishes as a product and falls back down to Earth, and stops reacting, here, if you look at the amount of energy that the firework had at the beginning, when it was packed full of firework chemicals, I needed some energy to make it react, and then it gave out a lot more energy than I needed to put in. I only needed to light it with a match, and then it gave out a load of energy as it shot into the sky and exploded. The products, the ash and the firework that falls back down to ground, has got less energy than it started with. Okay, so overall, if I go back to my equation where delta H is the amount of energy in the product, that's the firework, take away the energy in the reactant, which is here, it's going to be a negative value. Okay, let me try and prove that to you. Let's say the reactant or the reagent had 100 kilojoules of energy to start with. At the end, the products have got no kilojoules of energy. They're just dust. They're lying on the floor, no energy at all. So if I take the amount of energy in the products, which is 0, and I subtract the energy in the reactants, 100 kilojoules, 0 subtract 100 is minus 100. So you've got a small energy in the products, a large energy in the reactant, the firework, ready to be sent into the sky when I give it the activation energy. Products take away reactants, small energy take away large energy, gives a negative value. And that's why delta H, which is measured here, this difference here, from the energy that the reactants have, take away the energy that the products have, this energy here is my enthalpy change, and it's negative. If I use a catalyst, I need to put less energy in to get it to react. So my activation energy with a catalyst is lower. I need to put less in, so that's that value there, rather than the activation energy here without a catalyst. And then redrawing the graph for an endothermic reaction, the only difference is that the products have less energy than, have more energy than the reactants. So the reactants are at a lower level, and this product line here is higher. And then the two curves come across and down. It's just that this line is somewhere here, but these two curves come down and hit that there, and the activation energy for a catalyst comes down and hits that there. And when you take away the energy of the products, let's say that's 150 kilojoules, subtract the reactants at 100 kilojoules, 150 subtract 100 is plus 150, and that's why for an endothermic reaction that takes in heat, the enthalpy change delta H is positive.